Suppose I take a rod and I suspend it about a point. So there's this pivot point here, and I hook it to a thing so it can swing back and forth. Okay, so this would be a pendulum, only it's a pendulum with extent to it. The mass is distributed all the way along that. And I want to ask a question like, what is the kinetic energy of this rod? Okay, well, kinetic energy is defined as 1/2 mv squared, but now the mass is not at a certain point, and each piece of mass is not moving at the same velocity. If I break this up into sections all the way along this would have one bit of mass, so I call that, a little bit of mass. I can call it just m. And technically, I'd take this to the infinitesimal level, so this would be the teeniest of masses, or a dm. We'll just focus on these little pieces of mass, and then this piece of mass will have a certain velocity. And if I think carefully about it, this end would be moving a lot faster because it's going to go through a bigger arch, a bigger arc length than this little one. It's just going to move through a little one in the same amount of time. So these will have different velocities. Now, what's going to be important is where the mass is relative to the pivot point, wherever this axis or this pivot point is. Okay, so if we now think about it with this definition, we'd have to say, well, it's 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus ... Just keep on going for all the masses. And this would be infinitely long if we made these infinitely small. Okay. So this is going to be kind of awkward because all the masses are all, we need to identify each individual mass, and we need to know their velocities. Now, something that is nice is that though their velocities are different, the angular velocity is constant for all of them. Angular velocity doesn't matter. It matters what angle the object goes through in time, and these all go through the same angle in time. And so their angular speed is the same. So we don't have an omega-1 and omega-2. They're all the same. So remember that V is equal to R omega. Okay. The radius, or the distance from the pivot point to where the particle is, times the angular speed gives us the velocity of that particle. So doing that change, we have 1/2 m1 r1 omega squared plus 1/2 m2 r2 omega squared plus ... Okay. Since the omega is the same, we can pull that out, and we get a 1/2. And I'm going to pull the 1/2 out too. Put brackets here. I'm left with an m1 r1 squared. Here I'm left with an m2 r2 squared plus ... And I've got this omega squared that pulls out at the end. Okay. Well, this is something that doesn't have anything to do with how it's moving. The motion's right here. This simply has to do with where the mass is. Where is mass 1? Where is mass 2? So on and so forth. So this is a geometric property of the object alone. And we call that the moment of inertia and give it a variable, I. Big I. Okay? So I is called moment of inertia, which is a kind of difficult term to digest, but basically I like to call it rotational mass. Rotational mass. Okay? And we're going to find that we're going to have a lot of different rotational equivalents of linear stuff. Okay? So this is our rotational kinetic energy. We call that K rot. Okay? That is rotational kinetic energy. The energy associated with something, some fixed object. So this object has a rigid object, not fixed, sorry, a rigid object, so it can't bend or something like that, is rotating. All its parts are rotating at the same angular speed. This would be its kinetic energy. Okay. Now, if I had an object that wasn't pinned down, but I just threw it, then it would have a rotational piece and a translational piece, the center of mass. Okay, we'll get into that a little bit later. But one thing that's important is this I is a function of the mass and where it's located relative to some point that we care about. In this case, I'm caring about this pivot point here. But we technically could choose it from any point, which we'll find some advantages of that later on. But you can think of it as just simply rotational mass. Wherever you saw mass in a translational problem, a linear problem, or just a regular velocity or acceleration or force problem, you could replace it with I. We're going to get something called, what I'll call rotational force, which is a torque. It's just like force, only it causes a rotation. And it's inversely proportional to the acceleration is inversely proportional to this I, this rotational mass. So I is where the mass is distributed relative to some point.